Hi everyone, my name is Lydia, and this is what I wish that taught me about econometrics and introduction. We spent several videos learning what makes a valid instrument, but even when an instrument satisfies both relevance and the exclusion condition, one important question remains. Does it affect X strongly enough to be useful? Okay, so an instrument can be technically valid, satisfying all the conditions, and still produce unreliable estimates. And that's exactly the weak instrument problem. So the relevance condition requires you simply that the covariance between your Z and X not be zero. Any non-zero correlation is going to satisfy it. But how strong does that correlation need to be? And the relevance condition is silent on this. It tells you the direction, not the magnitude, and magnitude, unfortunately, matters enormously, okay? So the way that you can think about it is you have a Z instrument, which is quite strong, okay? And then X and Y. And then you have a weak instrument, which is not that strong, okay? Both satisfy the relevance condition, but this one, is barely moving the X, right? It's barely pushing it. The strong instrument provides abundant, clear variation, while the weak instrument provides almost none. And IV can only work with the instruments that are basically provided. Now, if you recall, on the first stage of the 2SLS estimation, we have X equals to pi 0 plus pi 1Z plus an error term. And if this pi 1 hat that we estimate in here is very small, basically the instrument explains very little of the variation in X. And remember, this is very important. So weak instrument, then it means you have a P1 that is very low. And if you remember, the beta hat IV is sigma 1 hat divided by pi 1 hat. So that means that if this pi 1 is very, very low as a number, the entire beta IV is going to be quite high as a number because the pi 1 is in the denominator. So the noise basically that this sigma 1 in here might have had, gamma 1 might have had, basically just gets amplified enormously. The clean variation we've been relying on is almost non-existent. And the little that exists is basically overwhelmed by that noise. This is also why the walled estimator makes the weak instrument problem so visible. So a small denominator turns small estimation errors into large swings in the IV estimate. Now, suppose your instrument is distance to nearest university. So the typical exercise that we've been doing so far. If you have a strong instrument, then you're going to have 1 kilometer closer 2 years of education, okay? So this is quite a large push per se, okay? You've got lots of clean variation and IV works well. However, if you have that 1 kilometer just pushes it by 0.01 years, this is quite small, practically nothing. So in scenario B, the instrument is technically relevant, but the effect is so small that it's almost useless. Now the IV will be computed, but it will be extremely unreliable, okay? Students often think that a weak instrument just gives a less precise estimate. Okay, so this is one of the myths. A weak instrument just gives a less precise estimate. Now, technically that's true, but the problem is actually worse than that. Okay, so true, but it's worse. So problem one that you have, you're going to have large standard errors and your IV basically uses very little variation, so your estimates become very noisy. And problem two is going to be that you have unstable estimates. Small changes in the data will produce large swings in the beta IV, so the estimate is not robust. You also have a third problem, which is finite sample bias. And this bias is towards OLS, which means what is happening is in large samples, IV is consistent, so it converges to the truth, but in finite samples with a weak instrument, IV estimates are actually pulled towards the OLS estimate. Now, why towards the OLS? Because a weak instrument barely separates the X, so no separation or barely separation from X hat and the X. So the predicted values of X hat are almost identical to X itself. So the second stage regression basically is almost the same as the OLS. The weaker the instrument, the more IV will resemble the OLS, which is exactly the biased estimator we were trying to escape in the first place. Okay. Is there a way to detect a weak instrument? Well, you can go back to the first stage. So if you remember, our first stage is pi 0 plus pi 1 z plus some error term v. You can do the standard diagnostic in the first stage. So you look at the F statistic. And the F statistic tests whether the instruments jointly explain a meaningful amount of the variation in X or not. So basically, a small F would probably be an indication that the instruments barely moving the X. Okay. You can use the 10 as a rule of thumb. F being smaller than 10 would be concern about a weak instrument. Now, this threshold, because I know we've mentioned it in a lot of videos, and I know a lot of you already know it as a rule of thumb, even without actually touching any of the econometrics books. But the threshold for this one comes actually from Steiger and Stock from 1997, who showed that with F smaller than 10, IV estimates can be severely biased towards the OLS, and standard confidence intervals also become unreliable. The F being exactly 10 is what corresponds to the maximum IV bias of roughly 10% of the OLS bias, which is considered an acceptable threshold in most applied work. But below F10, the bias can be a lot larger. But let's say for a moment that F is actually greater than 10, which is a useful starting point, but keep in mind that's not your final word. You also have other formal approaches, which include the Stock-Yogo critical values, and another one, advanced, apologies for the pronunciation, but Kleibergen-Popp Again, pop statistic. You can use the Stock-Yogo critical values because these provide F statistic thresholds that depend on the number of instruments and the acceptable level of bias or size distortion. Or you can use the Kleinberg pop test statistic when errors are non-spherical, meaning you've got heteroscedasticity or clustered errors, okay? So more robust than the standard F statistic in those settings. But keep in mind, these are additional ones which are mostly used for published research, for introductory applications, and also for your dissertations. The F being bigger than 10 is more than sufficient, okay? Although most journals nowadays, they do require reporting the first stage F statistic alongside the IV result, but some do require all of these other test statistics very explicitly. So just keep that in mind. Now, if we had a decision tree, what would that look like? Well, if you have a valid instrument, okay, it would mean if we go yes, that's great, this is what we want. The next question would be, is it strong enough? Okay, and if the answer is yes, it means you have reliable IV estimate. And unfortunately, if the answer to this is no, it means that you've got a weak IV, which is unreliable. Okay? Both conditions must be met, so a valid but weak instrument is not good enough. A strong but invalid instrument is also not good enough. Think of the instruments as trying to push the X. So a strong instrument gives X a firm, measurable push. A weak instrument barely nudges it. So if the nudge is tiny, it's extremely difficult to measure what happened to the Y as a result. And any estimate you produce will be dominated by noise. A weak instrument causes your IV estimates to be unstable, imprecise, and biased towards OLS, which defeats the purpose of using the IV in the first place. So going back to all of these three problems that we mentioned in the beginning. With this, we've completed the full conceptual arc of an instrumental variable. We've talked about endogeneity, instruments, conditions, 2SLS, OLS versus IV, the Haussmann test, and then implications of weak instruments. In the next video, we implement everything in R. So stay tuned, and I'll see you in the next video.